What is up, everybody? Welcome back to my channel. This is Tony, aka One Lead to One Day. If you're new here, this channel does one lead code per day, following the pattern of topics or series. That is, I'm going to be solving with you together on a lead code problem I have never attempted before. You heard that right. There's no prescripted answer. We're on the same page here. But don't you worry, I got you covered, and I promise that I will submit at least an average performance code at the end of each video. Here's a little bit about myself. I come from a non-computer science background, so I am no better off than most, if not all of you guys, in terms of coding knowledge. But that is okay. If I can do it, you can do it. It is all about learning on the go. You can think of this video as a first-person gameplay of cracking leak codes. And who doesn't like first-person gameplays, right? So without further ado, let's start today's problem. Today we continue on series 1, everything about dynamic programming. And we're looking at problem 45, jump game 2. And this is a continuation of the previous jump game 1 that we did in our last video. So let's just take a look together. Now, this problem, let's read it. Given an array of non-integer, non-negative, non-negative integers, nums, you are initially positioned at the first index of the array. All right, each element in the array represents your maximum jump length at that position. Right, your maximum effort. Your goal is to reach the last index in the minimum number of jumps. You can assume that you can always reach the last index. Okay, so this is actually something I guess a little easier maybe, because you can assume, if you can assume that you can always reach the last index, then there's no like problem existence problem. So there won't be cases where there are like sinkholes in the middle, and um you have very low numbers right before that, so that you cannot really get across those zeros. So that's not the case, but this time it's focused on um, minimum number of jumps. So your cost is the number of jumps you use. And therefore, using maximum effort is actually going to be helpful here, because if you use maximum effort wherever you can, you're more likely to use less number of jumps, right? So with that understood, let's look at example 1. We have 2, 3, 1, 1, 4. So if we just intuitively take some jumps, for this one here, let's say we actually take one jump here because we want to, exploit that number 3 there. So we can jump 1, 2, 3 all the way to the end, right? So it's going to take 2 jumps. Yeah. And then here, 2, 3, 0, 1, 4, same, because you're going to take the first jump and then take 3 jumps. Take 3 steps. Okay, constraints, you have a minimum of one step in the array, or maximally 10,000. And then the value, sorry, the potential, or like the maximum number of jumps you can perform at each step, at each index, could be 0, which is like a hole where you can get stuck, or it's 1,000, which is, a lot, so you can really take a huge leap forward. All right, so there we go. We have that definition, and we're just going to create simply create a similar problem and build our test case here. Let's start a notebook and just paste the basic information here. The problem and an example. Here we go. And we're gonna copy the solution template right in here. And then we use Alt Enter, right? Alt Enter to make a new section. And then we're just going to build our solution templates. Sorry, our test cases. Well, let's name it. Name it today's problem number 45. Jump, right? Lead 45. Might as well rename the previous one that we forgot to rename. Previous one was lead 55. So lead 45. Okay. So we're gonna take some templates for test cases here and paste it here. Test cases, and we're gonna use this test case from our first example here. Oh, it happened to be the same. So jump, and then we expect how much too, right? Right. So, all right, we have the problem here. It's a problem where we have an array of a list of numbers like this, and we start from the first one. And the number at each index means the maximum number of jumps you can perform to jump forward, or the maximum effort that you can use at each step. Maximum effort, right? You hear that a lot in Deadpool, I know. Here we go. So we have to come up with our dynamic programming recurrence relationship before we do anything else. Um, that means we're gonna use our sketchboard and start sketching something here. Now, problem 45, jump game 2. We can just take our first example here and then try to come up with some quick solutions as a baseline. Then try to improve the computation complexity upon it, right? That's so that's the usual, workflow that we're gonna use in our videos. So we have these problems, and let's say we start from this one here, right? And we can jump one step or we can jump two step. Uh, and then once we arrive at some other indices, we can read the maximum effort there, and then we can move on, right? So here the thing we want to find, if we want to establish as a DP problem, excuse me, the wire got in my way, is we want to, so this is our original problem, right? I would usually like to use S0 to represent our original problem, and the 0 means some kind of an index that we use to label our subproblems. In this case, because we always start from index number 0, and we have to reach, we have to reach this index, the last index. So our subproblem is probably gonna have the latter part of the list, and that is something in common for all the subproblems. So we can use where we start. We can use the first index as the label of our subproblems. So for example, the original problem is going to be 23114, and we start from 2, right? And for example, if we take out the right? If we take out the first element here, like this, let me just make the fonts having the same size. Then this is going to be what, in terms of our convention of calling subproblems, this is going to be called S1, right? Because now we start at, the original index 1. So if we say index, this is 0 indexing, so it starts with a 0. So we have 0, 1, 2, 3, and 4. And now we start from 1, 2, 3, and 4 because the value at index 0 is removed, and therefore we got the subproblem. So here's the subproblem. We still end at the same element, or trying to end at the same element, the same index. But this is a subproblem. So apart from the fact that the starting index is different, everything else is the same. And that is something we want to make sure. We want to make sure that the subproblems are in principle exactly the same in terms of format um, compared to the original problem. And the only difference is the number of elements in it is like less than the original one. And that is how we can apply the same rules of recursive solutions of dynamic programming. And that's how we can exploit the solutions of subproblems to solve the original complex problem. Right. Uh, right. So, and because right now we're minimizing, the number of steps, right? So we're gonna call it what? N uh in A, right? A is like action, right? Minimize the number of actions that we take. Yeah. So this is the goal here for jump game number 2. So can we just, for example, solve this simple problem using the dynamic programming heuristic? Yeah. We can establish something called a recursive relationship uh, to define our dynamic programming recursion, right? So our recursion relationship is going to be like this. Just looking at these two, can you express S0 in terms of S1? Can we do that? Well, you see, um, S0, this guy, what kind of options can we perform for the first jump? Well, we can either jump 1 or 2. So there are for S0 there are how many options? If the value at that index is marked n of index, so n0 in this case is like 2, right? So we have 2 possible options. So, 2 possible actions, 2 choices, right? And for each of the choice, uh, we can end up in a new state or a new sub problem. And then we're gonna basically use the rule of like maximization to sum it up to find out the value function or the cost or the optimal cost at the at the 0th step or for the original problem. But we can, you know, um, we can exploit the idea of using maximum effort because we're trying to minimize the number of steps. So naturally, we want to use the maximum effort whenever we can. So for example, we can start this by saying S0 equals, so we first try taking one step, right? Taking one step, uh, taking 2 steps at the first index. So it's gonna cost us like 1 jump, but we jump 2 steps, right? So those are the different terminology. We take 1 step, but in that one step, we jump two. Oh, sorry, take one jump, but in that jump, we take two steps. So we jumped two steps. Um, and then we're gonna end up with a sub problem at uh, 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 actually, you know what? I'm just gonna say take an action of two, but and that's gonna be like the arc cost. But arc costs are the same, right? So it's gonna be one anyway. So we're gonna end up at S012 S2. Or another option is that we can just jump one step, and we are going to have an arc cost of A1, which is still one, because the cost of each step, if each jump is the same, and then plus S of 1, because we land at index 1 in that case. And we want to minimize uh, 2 of that, because we want to find the minimum cost, right? And that's for the first step. We only have two terms, but the expression will change if we have a higher value or a lower value uh, here as our number of jump options. So that is that. Um, so we do not have you know we do not have the luxury of having a uniform expression for the recursive relation. It depends on the value here. It depends on the value of n k. All right, so we can do DP in a bottom up approach or a top down approach. Uh, Theoretically, the bottom up approach will save a little bit more on the space complexity, because we don't need to remember the numbers during the recursions. Because if we build things from bottom up, that is from right to left, we don't need to remember recursions. In fact, we will never have to use recursions. Uh, we just read the stored computation table, uh, and each time we do that, the value that we need are already there because we did things in a backward way. So that's what we're going to try to attempt first. That is, we're trying to attempt using a bottom up, bottom up DP in our first attempt, right? Um, so what we're going to do is we're going to start from the last. And now we're trying to use general symbols instead of numbers to generalize it. So we're going to start from, let's say, S of, because now if we use symbols instead of numbers, this is going to be n minus 1, excuse me. And what is n? Well, n is the length of our nums list, right? That is the length of it. So this is going to be 0, 1, dot, 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 and then minus 1. So Sn minus 1, of course, the cost of it is 0 because we're already at the end. And then we can move on to build Sn minus 2, right? Sn minus 2, and you know, because it's right next to something we know, uh, yeah, the only thing we know, um, we can simply say um, um, and also we're guaranteed that we can always reach the end, but doesn't mean that we can reach the end from all the points in there. So there are two different cases, right? So for this one, if n capital N minus 2 is 0, meaning if the value here is 0, then of course you're not going anywhere. So this becomes how do you assign it? The cost we're gonna assign it like infinity if it's like that, because if you land here, um, you're never gonna go to the end. So the cost is infinite. And um, if this n here is greater than 0, then the cost is 1, right? You just need to jump once. Right. And then let's try next one, n minus 3. So the third to last sub problem, something like this, right? Uh, and for that sub problem, we start on the third to last element, and we have to start there because by definition you start from the first index for any subproblem, just like the original problem. Uh, so the cost of that, it depends on the cost of uh, Sn minus 2 and Sn minus 1, right? Also, we're gonna look at, for example, what is your maximum effort and how much of those things you can reach. So for this one, we can only jump once because, right? Because well, we're still gonna take all the cases, right? If, for example, if n minus 3 is equal to 0, we're not going anywhere, so this will be infinity. Uh, and if it's greater than 0, then if it's greater than 0, we're gonna see what is your maximum, right? Now we're gonna uh, depend on how many options you have, right? So you could, if let's say, if this thing is 1, whoops, sorry. If this thing, uh, yeah, ew, I don't know what's going on. Let's use that. But okay. So if this thing is 1, then what happens is that you only have one option. That is go to the next. So it'll be, wow. Whoa, my drawing board is really throwing me some tantrum here. Uh, I don't know. Maybe it's out of battery. So I'm gonna pause the video and deal with that. All right, hopefully I fixed it. Well, what am I gonna say? I'll pause it again. All right, I am back. Turned out that uh, my sketching pen had a battery issue, so I charged it for 20 minutes. Hopefully now it works. Well, it's still not working properly for some reason. Let's try this. Let's try open the document again. Still does this weird thing. Okay, now better. Anyways, so if we work on Sn minus 3, no, this is not going to work. This is not going to work. All right, I'm just going to use my mouse for today. Sorry about that. So if Sn minus 3 is, right, if n equals to 1, then we can only take one, jump one step, and it'll become 1, the arc cost of taking one jump, plus whatever is the sub problem subsequently. So it'll be S3, which is Sn minus 2, right? When that is like that. And what if n minus 3 is 2? So we can jump either one step or two step. Then it'll be, of course, 1 here. But then we're gonna have, in addition to this only one choice, uh, we can have uh, we can take the minimum between going one step ahead, which is gonna give us uh, the same as n minus 2, right? Or we can take two steps, and then it's gonna give us s n minus 3. That is if n equals to 2, right? So we see this pattern, and then of course we can move on um, to other values, but we seem to see a pattern here, and the pattern is that the more choices we have at each index, um, actually the more computations we need to perform. So there will be more cases inside the min function bracket, right? Um, and we do have to test each one of them. So the complexity, the speed, the time complexity of this problem will be unfortunately, let's say, O n squared, O n squared. Yeah. Um, so this is something what I am a little bit concerned about. If we have a time complexity of O n squared, we're probably not gonna pass on the Leetcode test cases, or even if we could, we'll rank very low on um, the solutions in terms of time complexity. So what can we do? What can we do about that? Is there a way? Is there some I guess problem dynamic, problem specific insight that we can use to reduce the number of steps that we need to calculate during the DP? If there's something, if there's some insight that we can further spot um, to make the problem simpler. Um, this is a really hard thing to think about because one would think that dynamic programming is an established um, algorithm. So if you want to actually improve upon it, uh, it'll require some theoretical breakthroughs, right? That is way beyond what we can do here. So our best chance is to actually um, look at the problem in a different way, uh, to have a different view angle of the problem. So maybe um, you know avoid calculating stuff that we don't really need, and that would save us some computation. And because we're in the end looking for a cost, right? Uh, and building that cost map, building that cost map really does require um, every step in the dynamic programming. It doesn't look like we can skip steps. It doesn't look like we can skip steps. Unlike previously in Jump Game 1, where you know the problem is either true, you need to return either true or false, and you don't really need to calculate, um, continuous or accumulative costs or rewards. That that actually could be a thing that we could exploit and use to come up with like a very simple and powerful insight, um, which led to a solution that is faster, more efficient than dynamic programming. But it is probably hard to come up with that kind of solution here within 30 minutes or an hour. It would probably take a genius to actually do that. Uh, I'm pretty sure I'm not that genius, so uh, you know I don't think we can do that here. So we're gonna just stick with the traditional dynamic programming way of thinking, and then just use the bottom up approach as our way of optimization. And uh, uh, and that is it. I mean, there's nothing that I can think of to simplify the computation. So let's just implement it, okay? We're just going to use the bottom-up DP like this to calculate our result. So if we generalize it, then let's come up with some kind of generalized equation, right? So our S of, say, k minus sk, right? It would consist of several cases. First, if it'll be infinity if uh, n of k is 0, right? That's the first case. And sk equals 1, which is like the arc cost, because if you're gonna jump, you're gonna take the cost of that jump. Uh, and we're gonna take the minimum of the next landing states, right? So next landed states, next possible landing states, minimum of costs, actually cost to go of next possible landing states. And this is the general equation that we have. So the more next possible landing states we have, uh, the more comparisons we have to perform here. And we can, and because the number of jumps, they always include 1 as the minimum jump, right? It's going to be 1, 2, 3, all the way up to the maximum number. So um, so what do we mean? That is sk is going to be equal to 1 plus min of, for example, sk plus 1, um, sk plus 2, and so on all the way to sk plus uh, um, um, whatever nk takes us, whatever nk takes us. I'll pause for a bathroom break. All right, back from the bathroom break, and we're generalizing this. So this becomes, yeah, 1, which is the arc cost, plus the minimum cost to go of the next, excuse me, the next cost to go of the next states. So all the possible states that we can cover within our maximum effort are sk plus 1 all the way to sk plus nk, because our maximum effort is nk. Right. So we're gonna just implement this here. Uh, right. So this is gonna be our solution version, probably number 1. Version 1, bottom up, DP, without recursion. So the expected time complexity is O n squared. Expected space complexity is O of n. So what we're gonna do is we're gonna initialize again using because this is Python, we're gonna still use dictionaries. That's an efficient way to look up. So use s, and then we're gonna initialize it as an empty dictionary to store the subproblem costs, right? Yeah. And do we initialize it? Like if, yeah, we're gonna take actually n as the length of nums, right? And initialize. And the first value that we're gonna pump into it is gonna be n minus 1 as the key, and then of course the cost is 0 because we're already at the end of it. And you know what? We're then gonna use a for loop to go all the way from n minus 2 down to 0. And in this case, the way we build our self, yeah, we're gonna definitely make it a, are we gonna make it a class property? Not really, because if we just have one function here, we don't need that. Sk equals, right, there are two different cases, right? So case if that value is actually 0, then the net subproblem will be infinite, because we can't go anywhere if there's a 0. Right. So if nums of k equals 0, this is like a sinkhole. And if we start from this sinkhole, we're not going anywhere. So the cost um, of it would be Well, we cannot do inf, so let's do none. Else, if it is not a 0, then let's do 1 plus the minimum of the sum of the remaining values, right? Else s of k equals to 1 plus, well, for the min, for the min of s k plus 1 all the way to s k plus nums k. For that, we're going to, let's say, uh, yeah, if we don't want to use a lot of memory, for, let's use p, right? P in range k plus 1 all the way to k plus nums k. And then plus 1, right? So that we're going to end at k plus nums k. For that, we're going to find the minimum of those. Min cost to go. It's a temporary variable, right? Min cost to go is the minimum between itself and s of k, s of p. But then we need to initialize it, right? And how do we initialize it? Well, min ctg, let's initialize it with like a very large value. Because the largest value can be like 1,000, and the total length and the constraint is like that. Yeah, we should probably type in the constraint here as well. Constraints. So what kind of cost we can assign it? Let's just assign, for example, 1, 2, 3, 4, 5, like a very big one. Initialize. And then we're going to find the minimum of that. And after that, we're going to assign s of k to be 1 plus this. And I think that is it. And what do we return? We return s of 0, right? Yeah, that's what we return. And we're going to do the test case. Ooh. We've said we're gonna do the minimum. So let's see what went wrong. What went wrong here? Um, we're gonna just go from here. Uh, right. So k is equal to 3 because we're gonna start from the last to the second to last element, and then because it's not 0, we're gonna try to find out what value to assign to s of 3, right? S of 3, actually it should be 0 um, because SP, it should be S4. Yeah, S4 it'll be 0. So for P in range of that and that plus that, what is nums K? Nums K, nums 3 is 1, right? So this will be K plus 1 all the way to K plus 1. I would think it would work, but apparently there's some misunderstanding I'm having for the range function. So let's just say range 1, 1, 2. Range 1, 1, 2. So for I in range 1, 1, 2, let's print I. There's nothing, huh? Why is that? Why is that? I have a misunderstanding of the range function in Python. So what is the first and second element? Start, stop, step. Oh, okay. So the step is the third input parameter, not the second. So start, stop, step. Got it. So start, stop, step. Okay, so I have always thought it's the other way around, right? So range function is start, stop, step. I always thought like step was the middle input argument, but I was wrong. Anyways, so now we know it should be like this. Um, so now the test case worked, but I think this is actually um, this is some kind of overhead that we can reduce. Anyways, let's try the next test case. So if we try this test case, it should give us this test case. It should still give us 2, right? Uh, well, there's a none type. Okay, that's the thing. So once we have a none, what does that mean? Like we have we had no solution. Well, in terms of cost, anyway I can do is to actually, instead of assigning none, we can just assign like a huge number there uh, to represent a high cost. So yeah, that works. A huge penalty. But then that's the first version. But this first version, like I said, it's got the time complexity of O n 2, and I think this is not optimal. And I just thought of a way to maybe um, reduce the time complexity. And I suspect this can do on if we can somehow kill this for loop, right? Let's think about it. Can we kill this for loop? Because it looks like we're calculating these values. We're just looking up those SP values like a lot, and we're we're just looking up uh, values in this range between k plus 1 and k plus nums k, and we're probably looking this up multiple times, too many times. Right. So is it possible, I'm thinking, is it possible to, reduce the number of lookups that we have to do? Let's use purple to make magic. See if we can actually make some magic here. You see, we are calculating, we're taking the minimum between the cost to goes for the remaining for the possible resulting states or sub problems. Um, but these sub problems, they have, their values are kind of stored already. Uh, kind of stored already in there, and it sounds a little bit like, for example, if we start from this, if we work on the subproblem S1, and then we start from here, right? This is like the subproblem. Um, when we work our way back and we work on this now, it seems like because this is 3 and we have 3 different ways to go for it, um, we're gonna have to compare the S value at each of these resulting states, which we probably have done like a million times uh, before. For example, um, let's say if this is 4, right? Then basically, except for this one, which is something new, then and that's something we have that's something we've done once before by comparing, the minimum between these 3, right? It's almost as if we can, if we can build another lookup table, and that lookup table is a two-dimensional lookup table, given the beginning and the ending lookup, and you store that value, then we can just, instead of performing a for loop to look up each time, we can maybe just, store the value and use the table and look it up later, right? So without recursion and the um, storing the results of min, s, let's say m, s, m plus 1 all the way to s uh, n. Well, let's use a different I, J, K, P, Q, uh, R, S, T, A, B, C, D, E, F, G, HIJKLMNOPQRST. Right, let's just say X and Y, right? Um, all the way to SY. We're going to store the result of that in a data table indexed by X and Y, so that we're actually reusing these calculation if they have been like um, if they have been used quite a lot. And it's going to be like a sparse table. We only create the ones that we actually use, right? Right, so we're going to be creating that sparse table. So instead of actually doing this, we first look up the data table. We're going to call this uh, memo, right? First look up the value in memo, right? If we don't have it in there, then we can just do the computation, um, and then after that we're gonna store, update memo of this new uh, entry, right? With uh, x equal to k plus 1, y equal to k plus nums k, right? So we're gonna call it memo, right? And it's gonna be an empty, yeah, data table for storing this value indexed by xy. We can use a tuple, right? Hopefully. Can we use tuples as keys? Python dictionary tuple as key. Is it possible? You can use a tuple as a key if they're immutable. Okay. We just need to know the answer of whether we can do it. And the answer seems to be yes, so we'll use that tuple as a key. So update that memo. So we're going to update memo of k plus 1 and k plus nums k will become this min ctg, right? So first, if we look up if, right, if this, is in memo dot keys, then we simply return sk equals to 1 plus memo of that entry. You know, else, if it's not there, then we're going to have to calculate it, and then we're going to update it later. Right, yeah. And this is the entire sequence. So what we did is that in addition to version 1, which is a standard bottom-up DP approach without recursion, having time complexity of O(n) squared and space complexity of O(n), here we are storing one of the most time-consuming computations, save the results of that computation in a table, in a data table. Um, and when it comes to larger problems, this is going to save us actually some time complexity. But the compromise here is that we're going to have to increase our space complexity. And the number of things we have to compute here is now suddenly what n times n, because now you're storing a lot in your memory table. So, worst case, this is going to be like that. So it'll be n squared, right? Yeah. Uh, so we initialize it here, and then when we need to calculate this quantity, we first look it up in there. If it is in there, we just look it up. And if it's not in there, we're going to compute that value, and then we're going to store that value in our memory. And we're going to return this anyways. So, right, let's try that test case. So it works. Okay, so I think we have two solutions. What about let's submit the first solution here into Leetcode and see its performance, right? And we're going to compare it later. Run code accepted. Again, this is the standard DP solution, bottom-up approach, but with n squared complexity. Oh wow, there's a what is this? A key error. So that's something we need to immediately fix. Let's include this test case in our test cases and see what's wrong with it. I don't know what you're expecting. I mean, um, we're expecting the cost here to be 1, right? Yeah, because we just need one jump. Let's see what we get. Okay, there's some problem here. All right, key error 2 is probably the same error in the first version as well. So it's a common error. I'm going to start with the first version and keep track of what's going on. Key error 2. So key error 2 for dictionaries, as far as I remember, usually is that means like an overflow of the key value, meaning that the key is there, not really there when you try to look up. So that means we may have encountered looking up a non-existent key there. Now let's try to put a breakpoint in there. Now we're trying to run this, all right? So what is P here? P is 1. And what is our S here? Um, S is a dictionary with one key, it's just one, right? And then value of 0. So when our P is equal to 1, I think we can actually run this. For the next step, now P has become 2, and our S doesn't really have that value in there. So definitely this is going to create the error. We got that. So we know where the problem is. So how shall we fix it? That's the next question, right? So look at this behavior. Basically, we're trying to look up right. So when we run this for the first time, use 2, 1. So the number of elements is 2. So for this for loop, 2 will have 2 minus 2. That'll be what? 0, right? And the last element we want to go is 0, so we're only going to work with 0. And this is like the step, right? Yeah. Remember, this is how the range function is used. And um, if nums equal to 0, so this is like a special case. But in our case, nums 0 equals to 2, so we don't really need to go into this. We jump to the else condition. And then we're gonna calculate we're gonna calculate the minimum cost to go of the next states. For this one here, um, the only possible next state is the last one. Um, so index 1, and that happens when p equals to k plus 1, right? Uh, and so we actually have um, a maximum effort that is like overflows, that it will lead us to um, places beyond the last element, and that is unacceptable. So there's basically too much energy. We're gonna jump over the terminal state, and that's not something we want. We basically want this to be at the minimum between this and you know n minus 1. We don't want this to go overflow, right? We just want this to go maximally to the last state, right? So let's try that, and let's try this. Whoa, why do we get that? We're getting a lot. We're getting a lot. So k plus 1 up to this. Oh, okay. So I think we need to go with this, right? Because the range value, you're gonna have to bump the last value up by 1 actually to make the range value function normally. All right, so I think we just fixed that. Let's see if we can have the expected answers. All right, so we're gonna fix that here as well. Fix the same code like that. And then we're gonna try to run the second version. And we do have the expected answer like before. So we submit again. All right, we submit again with that one little fix. Run our code. Got a pass. Run more test cases. Got a pass again. And we submit. I'm afraid this time, it's going to exceed the computation time limit. Well, it didn't, but yeah, it's really, really slow. Let's do it again. See if it's a little bit averaged out. But if it takes, more than a second, it's really bad. So really, this is pretty bad. Now let's submit our, you know, enhanced version 2, where we sacrificed a little bit of space complexity to get better time complexity. Let's see if this is going to buy us a little bit more advantage for more complicated problems. It's taking a couple of seconds. It's not really looking good. It's not looking good. Guys, it's taking too long. So maybe the space complexity actually has hurt more. Uh, right. It actually sucks more. We are no faster than others. So let me just try again. So version 2, I thought it was faster. but in fact it was not. We were looking up like a lot, but maybe there weren't that much to look up. Like, yeah, it's actually worse. So the lookup, I guess most of the storage here become wasted storage, right? Mm, that sucks. I mean, we tried. We were trying to, store these values as much as we can, but I guess maybe we stored it in the wrong format. But anyways, those are my submissions. I think at this point I'm going to go directly to the solution and take a look. All right, see if we can learn something from here. So we have a greedy approach. This is probably good, because the complexity, yeah, it's good. So this is the optimal approach. And then what do we have? Dynamic programming solutions. Okay, they don't even list the dynamic programming solutions here. All right, but we didn't come up with that greedy insight for this problem anyway. So let's see what the solutions say. To find the minimum number of jumps, the brute force solution would be to exhaustively test all possible routes connecting the start and the end of nums. This can be achieved by backtracking. If you're not sure about how backtracking works or how to implement backtracking, you can go to jump game backtracking. Also, feel free to check out backtracking explore card. This problem is very similar to jump game, so we only need to make one change to the solution. Exploring every jump pattern that makes us from the first position to the last position, we must also keep track of the number of jumps. However, an exhaustive search would lead to time limit exceeded because we're literally finding every possible route and its time complexity is O2n in the worst case. A key observation is that we don't have to explore every route. Instead, we can find the shortest jumps by making locally optimal choices at each index, which leads to a globally optimal solution. Herefore, this article will focus on introducing an optimized solution, greedy algorithm. Okay, it's a good kind of greedy, like it's a global greedy algorithm. All right, um, we'll take a look at this nice intuition or nice, I guess, a nice insight in there. So intuition. Imagine that you are at index I in the array. The element in your current position defines the maximum distance you can jump. Right. Therefore, your next step will fall somewhere in the range start end, where start is the place right next to you and end is I plus nums I. Yes. The question is, where do you jump? If you're at this position in the array and you can jump to one of the following three places, which one should you choose? We don't know. If you're greedy, if you greedily jump as far as you can, you may end up in a place with small jump powers. If you choose to only jump one, you may have a strong jump power for the next jump. True. To answer this question, let's think about it in the following way. Our next move will fall somewhere between start and right. And to find the minimum number of jumps to reach the end of the array, we must determine which place will take us the farthest in the next jump. As you may notice, we're using a greedy approach, always jump to the place that will take us farthest. Greedy algorithms always make locally optimal decisions, which may or may not lead to the globally optimal solution. Therefore, we must test our greedy algorithm to see if we can prove that it leads to the global optimal solution. We will use proof by contradiction to verify that the greedy algorithm is correct. Our statement is if, at any step, we make a different choice than what our greedy algorithm would make, we can find a better solution to the problem. As shown in figure 3, consider two people, A and B, where A follows our greedy strategy, let's call it Alice, and B, Bob, follows the optimal solution. It's a hypothetical optimal solution. The number at each index defines the maximum jump distance. Yeah, let's assume that until this point, their decisions have been identical. And this is where the disagreement happens. Now that the choice they make for this jump will define the subarray for the next jump, the greedy solution always picks the largest subarray. Thus, A will always have a larger subarray than B. What do you mean by the largest subarray? Is it like largest by length? I don't know. What do you mean by largest subarray? Thus, A will always have a larger subarray than B. Henceforth, it's not possible to beat the greedy algorithm at any step and reach the end of the array in fewer jumps. This contradicts our statement. I mean, I see you're using proof by contradiction, but I don't see your point here. So the greedy solution always picks the largest subarray. So what is a subarray? So these three highlighted blue blocks are the subarray for the current jump. Yeah, subarray. So the possible states, possible next states for the next jump. Um, New subarray for the next jump. Why is it that for Alice we have 416 as the next subarray? Well, because Alice took 5, which is the largest between 5, 2, and 1 in terms of value, right? So for the next step, um, Alice can cover the range between 2, 1, 4, 1, 6. And Bob, for Bob to take any other, next states, meaning to either take the 2 here or to take the 1 here, then Bob is left with a smaller next possible states. It's true, kind of true, but it's still a little bit against my intuition. Like if we actually take the locally greedier solution of the larger value here, it's a 5 and a 2 and a 1. What if it's like 3, 2, and 1? Or if it's like 2, 2, and 1, what do you do then? If it's 2, 2, and 1, well, if it's 2, 2, and 1, you always take the next, the furthest, right? If it's 2, 2, and 1, you take the furthest, and that's not the problem. And if it's like 3, 2, and 1, well then you take the 3. It's equivalent to taking the 2 there. So, okay, I kind of like start to feel the intuition here. So the intuition is that in order for a an index, actually more down the line to be a better one, a better index than um, a previous than an index, earlier down the line, um, it has to have a value at least um, like at least you have to be, at most one value smaller than the previous one. For example, for this one to be better or equal to this one here, this 2 here has to be a 4, right? Otherwise, this value is never going to be as good as the previous value. So, right, I guess it is right. And this is like a very unique problem dynamic that we have here. And it's probably going to do the good job. So anyway, we have understood this. And I see that they have proven by contradiction that this is an optimal strategy. We're going to implement it. Right. So without looking at the solution code, we are going to write our own. So version 3, using the greedy intuition proved in solution, Leetcode solution. Right. So this intuition here is that we're going to always take the largest possible next element in our down our row. So what that means is that um, is that a bottom up approach or is that a top down approach? I think that's a top down approach. Right, that's a top down approach. So we're gonna let's make a new one. And we can start from, for example, k, k plus 1, k plus 2, k, k plus 3, dot, 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 and all the way down to, let's say, m minus 3, m minus 2, m minus 1. We can throw one more here, m minus 4. All right, so that's the array. And of course, we can have more values before k. But that's not our concern. Our concern starts with k. And this is our magic. So when we start with k, right, we look up n of k. So that is going to cover, a range of values. Um, you know, this is going to be like n of k values, n of k values, n of k options. And we're basically going to find the maximum of it, right? Like find the max value, find the max value in it, in the n k options. So what do we mean by that? What do we mean by saying that? So basically, we're gonna have to look up n of k plus 1. So n of k plus 2 all the way up to n of k plus nk, k plus nk. Yeah, so those are the values in there. And we're going to use a max function, right? Yeah, find the max of them. We're going to use a custom max function to basically iterate, use like a for loop to iterate through all those possibilities. And we just do this in a top-down approach until we reach the end. Yeah? Okay. So we got it. Now, here's what we do. First, we take n equal to the length of the nums list, and then we're going to use a for loop to go, actually while loop, because um, we're traveling, right? While our current position k is greater than or is less than n minus 1, meaning we have not reached our goal yet. We're going to, right, so initialize k as 0, initialize starting point, and when k is less than n minus 1, we're going to basically now follow this heuristic and find our nk options, basically find the maximum of these, right? So build our custom comparison for let's say p in range between k plus 1 all the way up to k plus nums of k. Nums of k, what if the nums of k is like a 0? It could be 0, right? uh if nums of k is 0, right? So what happens when nums of k is 0? If we have like a 0 somewhere, for example, if this one is 0, or sorry, if n of k is 0, right? If n of k is 0, uh, then we're stuck. So we cannot afford um, n of k to be 0, and because we're always looking for the maximum value in our next state values, we will never encounter this n equal to 0, right? It cannot be 0 because we are looking for the largest one, so we won't find a 0 in there if we're trying to maximize things. So don't worry about it being 0 because it won't, okay? For p in range k plus I to k plus nums k, actually plus 1, and then yeah, that'll be it. The step is by default 1, and then we're going to compare which one is larger, right? um, Max uh, uh, index is, if calling a max function is going to be expensive, then maybe we're gonna do our own thing. So yeah, if let's do it in this way. Um, if nums of p is greater than, right, we're also going to take into account the case when there are two values. For example, these two values, they all have the same value. For example, this is 4 and this is 4, and you of course take the further one, right? You always take the further one. So you want to kind of like encode this behavior into your choice here. So if nums p, and because we're checking in the ascending order, um, the new challenger is the one on the right hand side. So as long as it's like greater or equal to the previous one, we're going to take it. Yeah, so this greater or equal to takes care of that. Numsp greater or equal to the current incumbent champion. So max index. Then we're going to update it. Max index is going to be equal to p. Whoa, wait. Let's say, no, current max. Then, yeah, max index equal to p. And then current max equals to nums p. Right? We're gonna basically this is like update. Um, Index of the max number, maximum value. This is update the maximum value. Right. Otherwise, we keep going. And note, instead of here. This is important, right? Because when they are equal, you want to keep the larger index. And right, so we're basically doing that. And for each step, when k is a current position, and it's initially current position, right? Current index position. And once we've done that, we're going to move to jump to the max value. Jump to the index with the max value, maximum value. So how do we do that? We basically update our position, right? So k, we're going to update it with max index. And then we're going to count our jump count. Jump count is 0, and we're gonna update our jump count by 1. And right. And we're going for our maximum index, as always. And maybe we need to stop at some point because, you know, if we're already, for example, if we're already here, right? If we're already here, and then this says 5, right? Because previously you found that this is like the largest value, and you just choose to jump here. But then because it's 5 here, it's gonna go away 1, 2, 3, 4, 5. It's gonna go way beyond the last element. We're basically gonna have to tell it to stop because otherwise it's gonna overflow. Right, so once we're somewhere like here, basically we're just gonna need one more jump, right? Because the final step is within our reach. So we're gonna need a condition to say if, stopping condition, stopping criteria, if um, if the the possible maximum number of jumps of the current step uh, is and applied to our current index, if that is enough to reach n minus 1, then that is our second last stop, right? Exactly. So we're going to take that intuition um, and put it here. And k plus n of k is less than n plus 1, right? Yeah. So this is like um, when the last index is not yet within reach of one jump, right? When we're not at the last point and when we're not yet within reach of one jump. So when we jump out of this while loop, basically we just when we come out of the while loop, we are within one jump reach of the last index. So so we're gonna return basically jump count plus 1. Yeah. So let's just try that. Oh, there's something wrong. Oh, n is not defined, of course. It should be nums. What is it? Local variable cur max has not been signed. Okay, we have not initialized those things. So we need to initialize it, okay? What should we initialize them with? Because we're looking for a maximum. And these values are like they could be from 1 to they could be from oh these values could be from 0 to 1,000. So definitely we're going to uh, initialize current max with 0. Um, and what should we initialize our max index with? So the max index is what? The index of the maximum value. So it's between k plus 1 and k plus nk, right? Um, so when we initialize it, let's initialize it as k, shall we? Um, right, because it's gonna be overwritten anyway. But what if none of those if conditions work? Oh wait, we can initialize it as p, right? No, no, initialize it as k. Oh, okay. So actually we should put them one layer above, initialize them there, because the for loop is where the maximization happens. And after the for loop is where we actually got the maximum value. And for, yeah, when we jump to a different k, after, at the end of each while iteration, we're gonna refresh it and we're gonna update these indices. Okay, right. So this seems to work. Now let's send this to our Leetcode, say version 3, using that intuition. Run test cases, accept it, submit the code. Oh, okay. Again, this is like a special case where we only have one, value there. And this is no other than a 0. So we should expect what? We should expect 0, right? Because there is no steps expected. Right. So if n is equal to 1, we directly return 0, right? Right. All right, so let's just copy and paste this again and directly submit. Wrong answer. All right. So this is a new test case that's going to help us debug what we did wrong. For this test case, we were expecting what? We were expecting 2, but instead we got a 10. Is that right? Yeah, we expected not 2, but we got a 10. So what went wrong? What possibly went wrong? Well, if we were expecting like a 2 and we got a 10, that means we're calculating something wrong. Hey, this is a very typical one. You see, you should really just take the first one here and then jump 10 steps. And then you take just one more leap ahead. So why didn't we take the leap? Let's just put this into our analyzing draft, right? And we're gonna just try to figure out what went wrong with it. So we start from the first element, of course, and then we look at the value. It says 10, so that means we can choose between the next 10 values, and we're of course going to take the largest value, which is 9. Oh, I see. Yeah, then it's gonna really take all the values and it's gonna take all the jumps here, and then it's gonna take 10 jumps to get there. I got it. So this is not optimal. So when this does happen, how do you deal with it? Um, we clearly need to, like, for the next 10 values, right? For the next 10 values, we definitely need to look for the maximum. Um, but isn't it like this one has like the most advantage? Like mm, if you this plus 10, right? If we do like a plus 9, plus 8, plus 7, plus 6, plus 5, plus 4, plus 3, plus 2, plus 2, and plus 1. If we add, the number of jumps that we performed to the value there, it's like the total jump reserve we have for the next two steps. Yeah, this is a good concept. Like the total number of jumps possible, not jumps, the total number of distance possible in the next two jumps. The total distance possible in the next two jumps. I think this is probably by far the most correct way of representing what that is. We want to maximize the total distance possible in the next two jumps. And how do you characterize it? Well, let's just move this to the right, okay? Uh, so this can be expressed by total number of jumps. Um, this equals to what? Um, right, the jumps performed, right? So the P, like the jumps performed, um, plus uh, the value at um, K plus P. Yeah, so it is equal to that. Right, so P is the uh, distance used in the first jump. Right, so we're at each step we're trying to actually maximize this value, this quantity. And what this quantity is the total distance possible in the next two jumps, given that the decision of the first jump is determined. So it's going to be this plus this. So yeah, we're going to use red, okay? Yeah, the same red. So this is going to be 10, 10, 10, 10, 10, again 10, 10 again, 10 again, 10 again, but look, this is 11. So we're definitely going to take 11. And that is how we can skip this. Right, so this is like the updated version of this new heuristic. That being said, we're going to, right, We want to, maximize the total distance possible in the next two jumps. So P is the distance took for the first jump, right? Yep. And and we want to basically compare, right? P plus N K plus P. P plus N K plus P. Is that right? Is that right? N K plus P, right? Because, this is our K here. K plus P, right? Sounds about right. We did nums K, and now we can do nums K. Oh, P is already that, so P is already in like, okay, so we're gonna change that. We're gonna do range 1 to nums K plus 1. So if P is like, yeah, the distance we took in the first jump, and then nums K plus P, if it's greater than the current max, which is now 0 that we set it to, uh, and the max index is going to be K plus P. Actually, we're gonna do that. Additional index. Yeah, the index add to add to get the maximum value, right? Current max is gonna be nums K plus P. Hold on. P plus nums K plus P, because, right, so P plus nums K plus P. That is what we're trying to maximize, right? And yeah, if we found a new champion, the new maximum, we're going to just say, yeah, we're going to take that uh, as our new index, and the current maximum is going to be like that. And then once we found the best maximum, we're basically adding that to our current index, and then we increase our jump count by 1. I think we got it. Expect 0, expect 2. Yep, I think that's it. I think this is it. So let's run the code. It did work. Run more test cases. It did work. And this did work. Right, it's much faster. It's about 100 times faster than our second version, and it's about 50 times faster than our first version. And that's how powerful, a good intuition or heuristic can get you beyond like the standard dynamic programming approach. I guess this is like, the beauty in programming. You can always find something non-conventional that beats like a generalized algorithm, right? You can always find a hack somewhere in the problem to 10x, maybe 100x the performance of a code. That's why you always need, programmers, guys. So that pretty much is today's exercise. So to summarize, we had this problem of jump gate number two, which is a typical dynamic programming problem. You can still apply um, a bottom-up or a top-down dynamic programming approach to the problem. But since, the number of jumps you can perform, the number of different jumps you can perform at a certain state uh, is defined by the value in at that uh, at that index, and it's not fixed, and it could go up to like 1,000. So um, that means there are so many different ways to execute um, the current action. So this makes dynamic programming um, costly in terms of time complexity. It'll be at least O of n um, squared. Therefore, we always want to find like hacks to see if we can understand the problem dynamic better to get a better performance. And although we didn't work it out on ourselves, by looking at the solution, we realized that there is actually a dynamic we can exploit to make a very fast computation, and that is that you know um, and that game dynamic and that key insight is that we want to maximize the total distance possible in the next two jumps. Um, and by doing that, we can prove by contradiction that this is like the optimal strategy. I guess this is like looking, if you look at the problem in a different dimension, interpret the problem in a equivalent way, but in a more revealing way, then the problem suddenly becomes simpler to you and also to code as well. So that is what we did, and it turned out to be really fast. So if you look at our submission journey, the first one was wrong because we made a mistake, and then our baseline bottom-up dynamic programming um, worked, but it took, on average 5 to 6 seconds. And then we thought we made an improvement uh, by creating a memory table um, for one computation inside dynamic programming. So effectively trading space complexity for better time complexity. But it turned out that actually we spend more time doing that, creating the memory table, um, than just using the basic bottom-up uh, dynamic programming approach. So this was like a failed attempt. It was good, but it's a failed attempt. Uh, and then we move on to the solution, and we looked at this greedy, globally greedy algorithm or intuition that um, people have come up with, and we implemented a version of it. It's not exactly the same version, I guess, as what this is saying. Maybe it is, but I mean, I did improvise a little bit, and then we came up with this last sentence, like we want to maximize the total distance possible in the next two jumps. And when I implemented that, this just worked, right? This just worked, and we've beat like most of people in terms of runtime, and we're okay on memory usage. Let's just submit it again to see if it's still better. Yeah, again, uh, better than average runtime, but the memory usage is okay. All right, so that wraps up this episode. I'll see you in the next one. Happy coding.